Yeah. So last time, actually, we were discussing about Cassandra, and we did a lot of things. We saw how Cassandra is different than Dynamo, and in most of the cases, it is different, right? Yeah, but let's not go in details what it was. But everyone knows that Dynamo, Cassandra, both are classified as AP per cap theorem, right? It's like high availability for writes and partition tolerant, and it is optimized for high throughputs, right? So it has the same like a decentralized architecture what we discussed for Dynamo the same year, and only the consistency part is slightly different because in Dynamo we never heard anything about various levels of consistency, and it was just an eventual consistency there. But here we have different levels of consistency, and they are all tunable. So that is what was a different thing in this. Okay, so now also we discuss about how the data partitioning is. So it is again based on the ring structure. And so in Dynamo, we had whenever we had this partitions based on the hash values. So whichever node comes first with that token of that hash value, so that was considered a coordinate node. But in Dynamo, it is not. In Cassandra, it is not like that. So what happens is whenever a client request comes in, any of the nodes can pick up that request because they all are decentralized. They know about each other nodes, but they will forward the request to the correct replicas. But the node which first receives the request is actually called as a coordinator node. And that also does the other stuff of hinted handoff and all that stuff. But in Dynamo, it was like the main node or the primary node was actually considered as a coordinator node. So that was one more difference. So then we have in Dynamo, we have replication strategies. There are two different type of replication strategies. One is the simple and the other is the network. That was not there in Dynamo. So the network topology is like we have different replicas in different data centers. So that was the replication in Cassandra. So now I think we already discussed about these consistency levels also, but let's go through it a bit. And this is what the consistency levels or whatever they call it. It looks like in Cassandra. So what happens is if you see this table, we have write consistency levels and the read consistency levels. So it starts with any. Any means like the data can be written to at least one node. So it is an extreme case. So and all means like you have to write data to each and every replica. So in between that, it keeps on increasing. So in the second row, you can see 1, 2, 3. So you can, if you just look for the right consistency, so you can write to either a single replica or 2 replicas or 3 replicas like that, or you can follow quorum. Okay, so that will be a quorum based replication. And then you come to a local quorum, which means you can have a quorum on a data center. Frankly, I don't find any difference between quorum and local quorum, but yeah, that's a debatable question again. And then the second will be each. Each means you write on a quorum in all the DCs. Okay. So, and the last will be like write to all replicas across the DCs. So this was for write. In this case, for any, like if you have only one node, like, because all nodes are down, so you write on it. And hinted handoff is the way actually we can do it, because whenever other node comes in, the real node, whatever is supposed to be responsible for that request, then it has to return that data back to that node, right? So, but in the case of read, we don't have anything as any, so that is one difference here. And also they talk about read also, if you look at it, is almost the same. Whenever you want to read, uh, for the 1, 2, 3, you go for the closest of 1, 2, 3 replicas. Okay, so the closest is slightly different meaning, I would say here. Uh, it it may be like any of the closest replica on the ring, but also when you look for the response time, which node is actually uh, giving a quick response, okay, or low latency. That may be also one way of looking at it. So wherever we get a fastest response, so those nodes, and there are different mechanisms which is handled in Cassandra. We'll discuss that. So therefore, most recent data from 1, 2, 3 replicas, like that what they say, and the same thing for quorum also. Recent data from closest quorum replica. So closest maybe it's a physical also, rack based, or also the DC based. Okay, so now here in this case, when you go for local, then they talk about the current DC, and each it will be again for cross DCs also. And so for each, actually what it talks about, it's slightly different. In the right, it has to go to quorums in all DCs, but here it returns the most recent data from each DC. So maybe if some DCs have not a more recent data, it won't actually send from them, because that will be very expensive, because we don't want to have all the data which is not recent to come up to the node which is requesting in one DC, right? So we just want the most recent ones only. So that might be a way they are actually avoiding to do, or maybe exploit more of the network bandwidth, right? So that is the only difference what was discussed, like for any and in the each, they slightly differ in the read and write. Rest of them, they are almost the same. Okay, any questions till now?
So like quorum would be like global, right? I mean, the replica could be present in different data centers, and local would be local to single DC, right? I mean,
Right.
that could be different kind of.
Yeah. So when they talk about the quorum, it looks to me like a strict quorum. So based on the replication factor and whatever the quorum size you are having for the read and write, yeah. So that you have to follow, and that is what is, it will be local in a same DC or across DCs. Yeah.
I have one question.
Uh-huh.
Just if we say, so what should we say? Cassandra is used for write heavy or read heavy use cases?
Write heavy or read heavy? It's like high availability for writes, right? So it should be responsive for it should be responsive for writes, absolutely. But if we say that, then it will always be responsible for read also, right? So reads are always very fast response. That is what.
But whenever we pass a key, then only the read is going to be very fast, right? I would say.
Whenever you pass a read, okay.
Primary key, right, or something like that, because then only it will go with the range scans, and then it will return the response faster.
Yeah, right? I think there are different ways they are handling the read. We look that also, because they are using caching mechanisms to handle that. And yeah, but read has to be always fast, but write was always a challenge, right? So that is what they are trying to address in Dynamo as well as Cassandra, and high availability for writes. And yeah, the response also should be very fast.
Actually, I had one discussion today with some interviews. So I told them it is used for write heavy use case only, but they had some other views on that. So that's why I asked specifically in this question.
Yeah, so yeah, it has to be. Rights are absolutely important, right? Yeah. Yeah, Sharan, go ahead.
I'm saying, what was that view? Like, can you share? I think Gaurav was like.
Yeah. One minute. Some background noise is coming. Actually, the question is, I asked him a specific question. around he asked me a specific question around what you will use uh, uh, if you have to store the data, high throughput data over there, means data is coming continuously to you, and with no SQL database you will use. And if you have a high availability over there, so you want. So I said I can use Cassandra over there because I
Mhm.
can use it because this will support heavy writes and availability is there. But the interviewer was more of a concern that he said they want heavy reads. They have a heavy reads in Cassandra, not heavy writes. I thought it is heavy writes. That is the reason Cassandra is built because again it's all file. We are appending on a file again. It's again on LSM3 and all those stuff which is behind the scene.
Mhm. Yeah,
So
so it is written that way. But
yes,
read also are faster, I would say. But what
yeah,
he's looking for, maybe the use case might be very different, you know.
Maybe a read they might be saying because we have append only in the log, right? So the disk seek is very less.
Well, see, yeah, that is right. But see, the way the reads are handled, it's like they have different levels of cache also before going to even the mem table and the SS tables, right?
True.
So
Yeah.
if whatever is, but yeah, you will still have some latency because if you're not able to hit on those caches, then you will surely go to the SS tables, right? But still, they
Yeah,
have 2 or 3 different ways to handle that. Yeah, go ahead.
yeah, and even we can have to read many SS table for single key. Yeah, if we would have something like B3 index, we would be able to point in place on disk, yeah, by key. But let's say that we can have many layers of SS tables, and we sometimes we will have to read all of them. Yeah, so it's, I suppose that Cassandra is not as good for reads as Oracle or Postgres is good for reads because they use B3 index and not LSM. Yeah.
yeah.
Mhm.
For
That
LSM
makes
learner.
sense.
Yeah.
Yeah, that
But
makes a point. Yeah.
for write also it can be slow if you increase the number of nodes for write, right? Because from every node, if it achieves the acknowledgement, then only that would be a successful write. Like in case of all, consistency will be there, but again, write will go for a
Yeah,
toss
yeah.
time.
So in that case, what level you are configuring the consistency level? So that depends. If you configure it for all, then you are going to have a hit on that performance.
Right.
Yeah, but it again that is what the trade-off you have to keep in mind, right? Yeah, but then if you don't want mm, if you want to be very high available on writes, then you can actually choose 1, 2, or 3, whatever those were. At least that will be a decent way of doing it, isn't it?
Yeah, I mean, depending on use case.
Yeah, one instead of one, at least two should be better because one is almost like any, right?
Poor consistency kind of, yeah.
Yeah, yeah, yeah. So yeah, that was this thing for yeah these when we talk about the consistencies. And then we all know like how it happens whenever we get a read. So the read repair happens the same thing what we discussed for Dynamo. So we some way we have to fix the stale values of other replicas which have a stale data, and that happens at the read. So read repair happens there. So that is one thing. And now when if you look at the read repair happening, what is the main thing is so that is one thing what is being used, uh, which is called as a snitch. And that is what they say. It's an application which determines the most responsive nodes, the proximity nodes in a ring, right? That is why it is used. And so what I said, like when a Cassandra is performing a read operation and the coordinator sends a read request, it has to send to the fastest nodes, right, to get it very quickly. And if we have if we send it to 2 replicas, 3 replicas based on whatever the selection of our consistency level, So we would like to send it to the fastest one, and that is where the snitch comes into picture. So snitch is one application, okay, which gives us the information of the topology of all these the Cassandra nodes, and also the responsiveness. Okay, so based on that, you can intelligently select the node, and that is the way you can route the request. So you will get a quick performance. So, and then you can do a read repair based on whenever you get the value. So that is where the snitch comes in handy.
So what is this rack? Rack, I don't get. I mean, they use this term a lot. Data centers is like racks.
So you will have different racks in the data center, right? So your cluster can be cross racks, or it can be in a single rack in a data center also. So
Okay, the
it is,
nodes.
yeah. So it is like if you have the whole cluster in a single rack, and if the chances are the whole rack goes down, so it is always better to have the replicas distributed across racks also. So it can be distributed in the racks in the same data center or across data centers also. So that is what I get about these racks. So that is what I got this information here on this data stacks. So they talk about what a snitch is. A definition of snitch is it determines which data center and stacks racks a node belongs to, and they inform the Cassandra about the network topologies so that the requests are routed efficiently. And the topology is really important, right? Because that will actually determine the responsiveness, how quickly the uh, read request can be responded, or any sort of request can be responded, right? So understanding the network topology now, because we are dealing with cross data centers, so we need to know the network topology, as well as we need to know where a node lies in a rack and a data center, so that we can efficiently and intelligently have a replication strategy based on it. Okay, so now in this snitch, so that was the main definition of snitch. Okay, but then they have a lot of different things about it, and I don't think so it's required to go in details. But if someone is really interested in reading, so if you look at the snitches, the snitch is also a different varieties of them, and by default they say it's a dynamic snitching. That is what is used. So it monitors the performance and reads for various replicas and chooses the best replicas based on his history. So it keeps on maintaining a history. Okay. So how it maintains a history and all that, there are a lot of details about it, and that will be more of it. So now if you see, there are so many ways the snitch can be, and this is the simple snitch is actually it is mostly for development. That is what I was said in some places, because it doesn't uh, take into consideration data centers and all those things. And then we have others which are maybe very specific to some of Amazon EC2s, right? And then you have something very specific to Google Cloud, okay, or maybe Cloud Stack, Apache Cloud Stack environment, and all that stuff. Okay, so this is what one thing I found about snitches. Okay, any other, anyone wants to add to this? Okay, so if not, then the next thing what happens is the node actually, all the nodes in the ring, they communicate with each other using a gossip protocol, isn't it? That's what we actually discussed also last time. So everyone will actually find out if the other node is up or down based on the gossip protocol, and that is what we discussed last time also. So the gossip protocol is the same thing. It's not going to be different in this case also. So then the gossip protocol, we know it's a peer-to-peer protocol, and then keeps on passing all the uh, details of the state of each and every node. So and now if you look at very like, okay, so if we see here, it is an internal communication technique for our nodes in a cluster to talk to each other. And gossip is efficient, lightweight, reliable, and all that stuff. and it is decentralized, because that's what is the nature of our leaderless system also, right? And Cassandra uses gossiping for peer discovery, metadata propagation, and all that stuff. So it's just given an example over here. If we have these 4 nodes and they are gossiping with each other, these are the ways it can do. So basically it can go to each and every node in any direction. So that can happen, but this is very lightweight. So therefore it's not going to consume a lot of network bandwidth. So now if we just consider 2 nodes communicating with each other, the way it happens, it's like he is describing it as like a TCP three-way handshake. So the initial, if X is the initiator for the first one, so it will actually send some sync message to Y, gossip digest sync message, and then Y will actually respond with an ACK message to X. And then when he receives an ACK, he will actually, initiator will send another ACK2 message to Y, and that completes the gossip. Okay, so now if we look at the details about what SYN is, is a node initiating the round of gossip, which sends the SYN. So at this time, it sends about the compendium of the nodes in the cluster. So whatever nodes you have, okay, so that actually information is sent to in the cluster. What this initiator has, it is sent to the Y, in that case is the receiver, right? So it contains the tuple of the IP address of the node and the heartbeat version of the node also, the generation and the heartbeat version of the node. And then what does the ACK do is it takes this in message and then it compares that with its own metadata information, and then it sends it produces a difference message, and then that actually the ACK sends back to the initiator. And what this difference will have, it will consist of all the updated metadata information, which he calls as app states, that the peer has, means the one which received this request, but the initiator doesn't. Okay, so whatever he has, he's going to send it, the updated metadata version. So the initiator will know about it. And also the other part consists of the digest of the nodes the initiator has, but the peer doesn't have. Digest is like a checksum of the nodes. So whatever the checksum, based on that, he will identify what the nodes the initiator has, but the peer doesn't have. And then in the second, when it receives this ACK2, it will actually again take that information and updates its metadata with the app states for what he received from the receiver, and then he sends back the ACK2 with the metadata information, different metadata information of the peer that was requested based on the digest, okay, by the second what he was receiving. And this is the way both actually sync up to each other. They have the information of both of the, they transfer the information. So that is what it is said here. And then they talk about the gossip storm also, like in case when a node is going down and it comes up, so then there will be a lot of nodes actually sending in the request to the node which is coming up. So for that, how it is handled. So that is what being discussed here. So I think those things are, they are fine to be discussed, but so this is what it is. Any questions till now?
So it won't be n square messages, right? I mean, only random node would be chosen by one, right? One node will choose randomly.
Right, that is what, yeah, it will choose. And then that is the way it spreads the information. So, and then everyone actually will have that information and they stop communicating, they stop gossiping basically, right? Yeah, so yeah, one more, yeah.
I'm saying, when would they stop? Like when all the nodes have the same info, I mean, same metadata information, right?
Yes,
at that point will
what I look at is like when this 3 message handshake happens, so at least these nodes both are they have synced with each other and they don't have any messages to be transferred. then eventually, slowly, everyone will have the same message, right? Or maybe the same state. That doesn't make sense to transfer messages, right?
Yeah, that should be the point, right?
Hmm. But I got your point. That's very complex. I'm also not very sure because it might go endless, right? But I think there is some mechanism wherein whenever someone is actually heart beating at that time, he's sending a digest, right? So the checksum of what he has. So other is not responding, because he doesn't have to send, because whatever he's asking, and this node has, or he is also having it. It doesn't make sense. So that may be one way the X node may stop sending any request. So there may be some mechanism built because there is no central authority to decide on that. Yeah, but they have a seed node. What is they talk about?
Seed node is there. Yeah, seed node is there.
Seed node
And
is there for bootstrapping of a new node which is coming up. So whenever a new node comes up initially, right? So it is. Oh yeah, he says he's broadcasting for the initial digest. So that what happens. And for the seed nodes, that is what happens when any node comes up, there will be a gossip storm. So every nodes want to contact that with the new node. But that is the reason we are using seed nodes. So any new node coming up, so it will be given the seed addresses, okay, and then it starts uh, only gossiping with those seed nodes. So that is the one way it is done. Okay, so then other part what they were discussing is the failure detection. So failure detection is a very critical thing in this gossip protocol. The reason is because, so now how do you know a node is up or not? So it is based on the heartbeats. So what is said is like whenever a node, you check for its heartbeat, and then you look for that heartbeat, and then if it times out, then you will declare that node is dead, isn't it? But then the timeout of that heartbeat, if we keep it fixed, okay, so what is the timeout you have to select? If you select a very small timeout, it will be a good because it is very good time responsive and all that stuff. But the problem is that you might have what they call as like a false positives also, because there might be machines which are slower to respond because it is heterogeneous network, right? So all the machines, all the servers are not of the same capacity. So in that case, how do we handle it, right? So even if you think you are not getting a response from the node which you have sent initial SYN, but then if you don't receive any, if you declare that server is dead, but there might be another nodes which are slower like the same server, and they're able to communicate. So you cannot declare that server as dead. So there might be a lot of confusion. So that is one thing. And if we consider the timeout to be a larger one, so in that case, that is going to deteriorate our system response, right? Or the performance also. So for that reason, what they say is, it is very, what you say, like very tricky to understand how the failure detection is, okay? So you cannot do it on a very fixed basis saying, I have a timeout of very, very specific time value, and then I just rely on that. But then what happens, it has to, they are in this case, again in the same paper on data stacks, they have given a very good article about how failure detection recovery is. It's very concise again here. It involves a lot of details, but if we just look for our understanding here, this should be enough, right? So what it talks about here is the failure detection mechanism, why it is important. Okay, it is, first of all, it is a method for determining, locally determining the gossip state and a history of another node in the system is down or has come back up, right? So there is a difference between if a system is down or if it has come back up. So there might be a system which is coming up, okay, and also if you want to avoid routing client requests to unreachable nodes wherever possible. So because sometimes we might think that the node is not alive, but the node is really alive, but it is only taking a long time, right? So therefore, so all these things, how they are handled, and also, okay, they are also discussing about the failure detection using the snitch, dynamic snitch over here. So now the gossip protocol, what it does is it tracks other nodes, means directly, means just sending a direct message, or indirectly. Indirectly means a node is communicating with another node, and that node communicated with the third node. So that is the way you still get a data. It's the data is percolating from level wise, right? So whatever the data you collect, so if you have something like a fixed threshold of the timeout for marking failing nodes, it won't work. So what is a different way it has to be done is you use a accrual detection mechanism. It means that you what was talked about, like the history of the node, right? Based on how responsive the node is, that depends on different factors. So there are some factors that they are taking into account. Is one is the network performance for that particular node, so the workload and the historical conditions. So per node, so what is talked about, you don't consider a threshold of the timer as generic for each and every node, but each and every node will have a different threshold, and that will be based on the network performance of that node or the workload that node is handling, and all the historical condition. Historical condition means it might be a low capacity server, okay, or might be the server is not responsive always, there are some problems, but still it is able to cope up, or maybe it's heavily loaded because of the data what it has inside it. So all this, but you cannot suddenly stop that server and bring a new one. So, but you can still live with that. And for that, you have to actually adjust just your threshold based on what that particular node is comfortable with. Okay. So now that is what is done. And then they say you maintain some sort of a sliding window, and you just keep on maintaining whatever the gossip message you get in that. And that is what they say, that this is a phi convex threshold property, and then you keep on adjusting based on the sensitivity of the failure detector of that particular node. And so there are many details in it. So either you keep live with whatever the convex threshold, whatever has been set in that property, or based on the responsiveness, you can actually increase by some number of times. And that is what Amazon does. That is one example what they have given. It increases up to 10 or 12 times the threshold. So some of the nodes which are not responsive, they will still not be declared as a dead, because they might be doing some other task, right? Someone is just using that as a replica. So it's no harm to just say that node is dead, and then create a lot of confusion in the system, and then there will be some other system who's trying to handle all that. So in order to avoid that, so they just actually play with these thresholds, and that is the way to understand how the nodes in a particular whole network, which are responsive or which are not responsive, which are dead, or which are actually slow in response and all that stuff. So that is very important concept. Even if you look at it, it looks very easy. It's just a node, you just declare it fail, or you just stop sending the request, but it's not like that. So there are a lot many details involved in it, and that is one way actually they are trying to address over here. And I think this topic will be very huge. Okay, so this is what it is, everything about here. And then when they say, and then when a node comes back online after an outage, okay, so there might be different types of outage, right? So it depends on how the outage was, because it might be just a transient outage, or it might be like it has gone for a long. So based on that, then you will have to repair that node. So if it was a very transient outage, you can just handle that with a hinted handoff. But if it was the outage was more, you either use some different mechanism like a manual repair, because the hinted handoff also what we discussed last time, whatever the data it is keeping, it is just keeping based on some time window. Because if we keep too much of data in a hinted handoff in a coordinator node, it is going to be overwritten. And we don't want to keep more data in that also, because that will create a responsiveness. So therefore, the other way of handling or repairing a node will be use a manual repair or some other, they call it the node tool repair and all that stuff. And that is the way we, before declaring a node, completely permanently dead, so there are different stages of a node, states of a node, and that is what is being discussed over here. Okay, so they are trying to make the data consistent across the nodes. Even the nodes are less responsive or a quick responsive, so everyone has a different way it is repaired. So the whole thing is written here.
Yeah, I mean, so like this hinted handoff will, like, I think it will stay for some time, right? Beyond that, I mean, within that time, if the node doesn't comes up, which has gone down, that then I think like they start discarding the data, right? I mean, whichever
Yeah,
node
for
was
3 hours. For 3 hours they keep it. Yeah, because that is sufficient, 3 hours data. So if you have a transient failures, like if your node has gone down for some reason, it comes up, then it's good. You can actually return the data, whatever you have stored in the local database for that node, and that is enough. But if it's more than 3, then there is some real different problem, right?
True. Yeah, I mean,
So maybe either you completely remove the node and you are adding another node, right? So that will have to be differently handled. You cannot just handle it based on the hinted handoff, right? So that node has a different level of consistency. Yeah, the replication, whatever that state is, completely different. So you do either the manual repair or use some different tool. Yeah, that is what I got from here. Okay.
One is the sliding window of inter-arrival of times of gossip. Is it like the messages which are being transmitted among the nodes?
Yeah. So because every node is actually is transferring, and the node what I'm receiving. Okay. So my response time will be different, and the other nodes also response time will be different. So now I have to deal with that. So that is what they're saying. You use a sliding window, and so based on the sliding window, you consider the threshold. Okay. Or else if whatever threshold is not matching, then you have to increase that threshold. So that is what he's using, just a sliding window term. So just keep into account whatever the inter-time arrival comes in, and you don't respond within that, then the initiator will think you are dead, right? So you need to actually, maybe the initiator needs to understand that, so he will actually keep on increasing the threshold and then keep on sending the request again, something like that. So there are some different ways they are handling it. I think they are calling it something like that, the adaptive way of the threshold adaptive way, right? Historical.
Okay, based on the response, they might be changing the thresholds.
Right. Yeah. So I found this was an interesting one, and maybe more reading required. If anyone is interested in that, I will share the links. Okay. So now when we have done with this, so now what happens is we actually will go to the first is how data is written in a Cassandra node. Okay, so this is the way we'll start now. And I think most of us know about this stuff. So how is data written? So what Cassandra does is it processes data at several stages on the right path. So one is, the first thing is the data is logged into a commit log. So if you look at this diagram, so whenever we get a write request, so there are two layers. One is two regions. One is the memory and the other is a disk, right? So the data actually on a very high level, it first comes and is written in a commit log. So commit log is like a write ahead log, and that is will actually satisfy our durability requirements, right? So when the first time it has to be stored in a commit log, and then it will go to the mem table. So first it stores in a disk, and then it stores into the mem table. So mem table is like what they talk about is, okay, so before going there also, when mem table is full, then we flush it to the SS table, and the SS table is on the disk. So and mem table is in the memory. So now we have commit log in the disk and SS tables in the disk, and mem table is only one which is in the memory. So mem table acts like a cache in this case. They call it as a write back cache, right? So now, so when a write comes, so Cassandra stores the data in a memory structure called mem table. Okay, and to provide durability, it also stores in the commit log on a disk, and the commit log receives. It is an append only log, right? And therefore, if there are power failures and all that, it still survives. And then when it comes back, a node comes back, then it is read from the commit log and rebuilds the mem tables and all that stuff, right? So this is what it is. And the mem tables is written in a sorted order. And the mem table is written till it reaches a configurable limit. And then only it is flushed. That is obvious. Everyone knows about that, right? So now how the data is flushed into the mem table. So first it writes to the disk in the mem table stored or sorted order. And then there is a partition index which is mapped on the disk and for that particular token, and then it is actually set. But now, so to copy a mem table, okay, or flush it into a disk, so there is some configurable threshold. So it may be the size of that mem table, right? So you actually adhere to that, the configurable threshold, or you, if the commit log, the commit log space is also exceeding, then also you flush whatever your mem table is into the disk. And how it is done, actually it is queued. The request is always queued. It is not directly stored. So once it queues that mem table, so another new mem table is started, that will be an active one. And also they have said here, the mem tables and SS tables are maintained per table. Okay, and the commit log is shared among all the tables. So the commit log will be same for all tables. But mem table and SS tables, per table you have a different mem table and a different SS tables. So you will have n number of queues if you have a number of tables for mem table flushing to the SS tables. Right, and then they have given some more details about here, how the queue is configured and all that stuff, right? So we can actually read that later, right?
So
and
even
also,
your commit table will be full at some time, right? So then you'll have to use segment log to something, right? Collection of commit log, something like that. I mean, commit log will become full at certain time, no?
No, see what is said, see, data in the commit log is purged after its corresponding data in the mem table is flushed into the SS table. So whatever data mem table data is running, that only data is stored in that commit log. Commit log is also, it doesn't, it's not like you just append it and then you forget it. You actually also do some sort of maintenance on it, wherein whenever you see your data is moved to the mem table, you need to delete that from the commit log.
And then,
oh sorry, yeah, I mean, yeah, when it is flushed, when mem table is flushed to the SS table, because it is already in the disk now, right? So this data which was here, which was a mem table, the mem table acts like a cache now, right? So when the cache is flushed into a disk, you don't need the 2 copies of it, so you can easily delete from the commit table. Yeah, it's easily said, but it's not so easy also, right? Yeah, there will be do it.
That's
once commit log is full, they are putting many commit logs, something like segment of, I don't know exactly the name, segment of logs they keep, so that because there might be position when, let's say your mem table is not full but commit log becomes full, right? Then in that case, what will we do? We should have some alternative logs right here parallel to this, or we need to chunk this log. I'm not sure exactly here, but or maybe the size of
I got your point. Yeah,
something like that.
yeah, I also not read. Yeah, Nick, you had something to say.
Does Cassandra block new writes during the flushing process? So if there is flushing going, does Cassandra block writes, new writes?
It blocks the writes, right? A blocking queue. Okay.
Okay, so for that much amount of time, the system won't be available, right? Then, or that particular node won't be taking any writes I mean,
Yeah, it
giving
will
that
be
point of
it will be less responsive in that case. Yeah, that is what you can say. In that case, it won't be responding to writes, but some other node will pick up, and that will be committed by that the failure mechanism what we were discussing, right? Yeah. Yeah, so that is
So,
what said.
yeah, if there is one commit log for all tables, so will that not be a bottleneck?
Yeah. That's why I said that you have multiple log of, I mean, many commit logs will be there, which we call as segment table. I was thinking like that. But here,
No, but you're saying only one commit log per, I mean, whole tables, right? I mean, all the tables.
All tables, yeah, that is what it said here. Yeah, so that is a good thing. Yeah, maybe there is another thing inside the commit log, and there might be more details about it. Yeah.
otherwise it
But it's only append only log, right? So it has to be a single one, isn't it? So then
but
or
size-
else we'll have
if size is full, then how will you like? There should be something, right? I
so
mean,
if size is full, as I said, it's like you block the writes, then you don't do take accept any writes. So you just
but that means you are hitting the availability of the system, right? Rather than we could have created some parallel commit logs.
yeah, so
I mean,
it's a replica. So it's again a heterogeneous network. So some nodes will be slow in respond. So other nodes have to pick up. So that is one trade-off.
Yeah,
it is going to hit performance. That is right. But then you have to have the replication factor managed in a better way then. Yeah, but then that is one thing. So this is the way it is. But then how the bottleneck, is it a real bottleneck, or maybe how to handle that? I didn't read anything about that, but if you get any inputs, I'll share it. But if anyone has, please discuss here if wants to share any input. Okay, so mem tables, as I said, now how storing data on a disk in SS tables. Mem tables and SS tables are maintained per table and all that stuff, and SS tables are immutable. So they are not written again after the mem table is flushed. So that is obvious, right? It's immutable, and consequently, a partition is typically stored across multiple SS table files. Yeah, that is right also, right? Because your partition, it might be at different locations, so you'll have to store it in different S tables, and SS table structure exists to assist read operations also. That is also right. And then they discuss something about how it is stored in a Cassandra. There are three structures. One is the SS table data. Then you have a primary index, and I think the primary index is a combination of the partition index and then the cluster index and all that stuff, right? And there are different ways to handle that. And then there is a Bloom filter also. So this Bloom filter is usually in a memory, and it checks if the raw data exists in the mem table before accessing the SS tables on the disk. I think this is for read, right? We'll come to that later.
Deduplication, I think. I mean, to duplicate rows should not be there, right? That's why I think Bloom.
But this is more for when you read, because I think we are discussing about the write, but they are just mentioning it here. Because when you write, you have to write. There is no way, because you can have multiple same values of the same keys, right? And you might have doing some updates, and then you're updating the same value of the key. So you still have to accept it. So they are just mentioning it as a placeholder, or maybe the same structure you use for the writes also. And then the other stuff, yeah.
Yeah, for the writes, we don't use Bloom filter. Only for the reading, they use the Bloom filters.
Correct, yeah. That is what it is.
But they mentioned it for write here, right? That's why I thought
No,
that before
yeah. He doesn't mention, he says, a structure stored in the memory that checks if row data exists in the mem table before accessing the S tables on the disk. So that it looks like a right, yeah, read, sorry.
Okay.
Yeah, and then all the stuff what discussed over here. Okay, so yeah, anyone wants to add anything? Okay, so the SS tables are files which are stored on a disk, and then the convention of SS table has changed and all that stuff. So then I think we'll come to this later again, So because there are some more things also in this table which will cover during compaction.
Yeah, I think it makes sense to look at secondary indexes file. Yeah, so we can see that Cassandra does support secondary indexes, and I shared a link on Discord. According to this link, Cassandra uses Cassandra creates separate index for each SS table. Yeah, and
that offset you are telling, right? Corresponding to the offset, it maintains where is it present. I mean, you have a
yes.
data file partition index. Yeah.
Yeah, and according to that article, Cassandra uses B3 index for these purposes. So the secondary index is a B3 index.
So advantage is like you will easily go to the partition, particular SS table, right? I mean, what data, what offset it's holding.
Yeah.
Okay, okay. So that is an index. Okay, so you call it as something like a partition index file, or
Partition index file.
it is just for the partitions, right? Or
No, they help you to go to the given SS tables. Like a hash map will be there, which will keep like I mean, it will keep your this what do you say offset, and corresponding to offset, it will have a partition key. With the help of that partition key, it will take you to which index you will have to go into your SS table. So directly you can go in off one time.
okay.
Yeah, it's like LRU cache, I think, right, where you maintain the address of each of the linked list node, so that you look into the map and then go to directly the address, something like that. But B plus C, whatever was using, that's more appropriate.
Right, right. Okay, no problem. We'll get that, and maybe we'll have to revisit this later. So now the one thing what we would like to discuss is how data is read. Okay. So now data is read in Cassandra like this, because we know that data is at two places. One is mem table as well as SS table. So we have to read from both, isn't it? So, and also then they have like, it is again said, Cassandra processes data at several stages on the read path to discover where the data is stored, starting with the data in the mem table and then finishing up to the S table. And also it must combine the results from the mem table and potential multiple SS tables. So now, first is you check the mem tables, then it says you check the row cache if enabled. So there is one thing what they call as row cache. So that will be like the hot information, hotkeys and everything, or very frequently access keys. And if you enable this row cache, it will be stored there. So your actually request when it comes here. So this is what the row cache is here. And whenever your request application requests a hot or frequently accessed row, it just comes to this row cache. And then the rows per partition, if they are 1000, I think this is also configurable. So this parameter, so you can actually per partition, you can configure these. And based on the configuration, you can store that many number of keys. And then actually it just return back very quickly. This is the fastest one. Okay, now in that case also, but if the data of the same key is updated, so in that case it will be invalidated, right? And then again for the next read, it will be again it will have a cache miss, and then it will pick up from the respective mem table or the SS table. Okay, so that is the way the row cache will be handled. So, and then you check for Bloom filters before even going in the SS table. You need to actually check for Bloom filters, and Bloom filters actually give us either the data is not present, it will tell us, or it will say it may be present. Like it will give at least, it might give false positives, but it is at least gives us if the data is not present. So that is what Bloom filter is used here. Okay, that is very important because you have multiple SS tables, and then you need to really find out whether you have written into that for that key, or if that key is really present. So it might say either it is not present. If it says it's not present, it is sure it's not present. But if it says it is present, so it doesn't mean it is present. It might be present also, or it might not be present. But chances of being present will be more than chances of being not present. So therefore, it gives us more responsiveness in going through SS tables, or because going through SS table is more expensive, because if it might turn out that you'll have to go and look at multiple SS tables, right? So that is why it is. And I think when we come to compaction, we'll come to know about how SS tables are also handled in a much efficient way. Right. Then you check there is a partition key cache. Now they also talk about another cache. So this is the partition key cache. What it talks is when a read request comes in, first it actually goes to a Bloom filter. So if Bloom filter says go ahead, then it will go and first look in the partition key cache. So when if he says there is a the keys partition key is present, so what it will do is actually directly go to the compression offset. Okay, and then from the compression offset, it will get the location of the offset where it is stored in the disk. So it will just go to that location of that offset, and then it will scan for the key and then return the result. So that is one way. So if you don't go via this, if you don't find the key in the row cache, then at least you look for the partition key cache after you going through the Bloom filter, and then you can actually be slightly better than going directly to the SS table, right? So if it is not, then what is the other way is you go to the partition summary. Okay, so the partition summary is again still this as well as the partition key cache, they are all are in the memory only, right? So then this partition summary, as I think Nick was saying about, right, we have this partition index, it might be the same thing over here. So the partition indexes are again stored in the disk, but the partition index has another layer which is called as partition summary. So the partition summary is actually, you know, it is creating blocks of different partitions together, and then maybe it is doing a range-based partition, and the range-based partition starting token is stored in the partition summary. So if we don't find in the partition key cache, then if we look for that, if our partition is present in any of those ranges, so based on whatever the range we partition is present, so it can directly jump to that partition index offset. From there you can find the exact partition, and then you go and look for that partition offset in this compression offsets, and then you in turn it will go and look in the SS table and find that respective key. Okay, so this is what the flow is.
Yeah, this is what I was talking about. This partition key cache, it will take you to offset, and then from offset you can directly go to the SS table.
Okay. Yeah.
Yeah.
So
But yeah, but we can have multiple SS table for single key. Does it mean that partition key cache will take care about it? So we can have 10 SS table per single key. Yeah, we will have different offset and in different files. How to deal with it?
So for every key, it will give you an offset, right? And you will go to that offset in your SS table. I mean, along with the yeah, it will give you the offset, and corresponding to that offset, you go to those SS tables and pick the data. I mean, partition key is a range, right? It can have multiple offsets in it.
No, his point is like if you have, see now what it looks like here as per this diagram, that this data block, whatever it is like an SS table. If we just assume it, okay, it's a single SS table, and then we have this offset coming in. So what he says, if we have this block, many of them, right? And then if we come and see, if we hit on this and we see that we don't find it in this SS table, then do we move to the next, and how and when and how that is handled. So I think, you know, see the SS tables, if they are multiple, so the compression offset what is generated over here I think we will be discussing that when we do the compaction, I think. So this compression offset will actually have that offset. It's not only offset in a particular SS table, but it is actually looking for different SS tables also. So that offset will be respective to a particular SS table. So that is the way it will be built. So that whole flow will be handled by the compression offsets. That is what I think. Maybe I'm wrong, but Nick, you or someone whoever has the information, please give your thoughts on this.
Yeah, it should be like that only. Like for key, which all offset falls, right? Those offsets will be stored corresponding to that key.
Guys,
And when you
stop.
get the offset, you can easily go to the SS tables where those offsets are present.
Not able to save files to your external hard drive or your SD disk or your USB. Okay.
Come again, like I missed it. I think, yeah.
Okay. Yeah, so that is the one way. And then he talks about the fetches data from SS table on the disk, right? So that is the way you get, and then you return it. So this is the whole thing, right? So again, he has shown here, if you don't find in a row cache, right? So the other will be, you will have a key cache also. So that those key caches will be the one more layer. Okay, after a row cache, you can have a key caches also. Instead of going all the way to the partition key, you can also have a key cache. And then see if, oh no, he is talking about the same key caches here. Okay, so that is what the key caches are here. And then if it is not, then you go to the SS tables, and then so see now, if you find a key in the mem table, if you don't find it, then you, whatever the information you get from the SS table, mem tables, actually it is merged together, and then it is sent back, or whenever if you find something, if you don't find a stable mem table, then you can actually find in row cache. So that will be a quick way of doing it. Yeah, so there are different paths, and it's more complex. That is the way it is trying to depicting this picture. So even if you have a row cache, if you have key cache, you can have multiple SS tables on a disk, and then also that information will be on the mem tables. And also we know that it's an append only everywhere. We don't delete, but we have the tombstones marked for a deletion of a record of a key and all that. So that is handled differently here in this, because we don't delete everything, right? So we just mark that as tombstone, and then eventually it might be moved out, but at least that data will persist for long. So there will be multiple copies of the data, and then to converge on the right value. Okay, so there will be a lot of complex things happening. So this is a very high level flow what they are showing up, but there will be lots of details, and if we read into each and everything, we will get more about it, that, right? Okay, so here also they have mentioned most of it. Okay, so if someone is more interested, they can actually go through this. Okay, so this was, but I think we had a question about caches, right? So there is that OS level cache and how that is handled, isn't it? If it's a page cache. So I think what I found out was the row cache, whatever was talked about, can be like an OS cache, and this is the fastest one. And that is the reason all the frequently used uh, keys are placed in it. And then, as Shashank, you said, it's a LRU eviction policy, and that is the best way to do it, because based on the configuration, if we have a high configuration, then we'll have other problems, because we need more cache space, and that might be expensive also in some cases. So that has to be configurable. So how that is done, the evictions and all that stuff, that is also important. And as whenever data is stored in a row cache, and then that particular value is updated, so as I said, like it first goes to the mem table, And when it goes to the mems table, at that time, it will be invalidated in the row cache. And so whenever another request comes in for that particular key, and that will be a read miss, and then the data will, whenever it is read, it will be stored in the cache.
Yeah, one question. So what's the difference between row cache and key cache? They both look same, right?
So row cache is basically you have a key, and this key cache is the partition. So it gives you the partition. So the partition keys are cached in it. So it doesn't cache the exact key with the value. It's not a key value caching, but it's a partition key caching.
Oh,
So
okay.
based on
So
the partition, you have that offset, and then you go in that SS table, and from that offset, you find out the key's value.
In row cache, the entire row along with the columns, like the entire
everything
row
will be there. You will get the record. The complete record will be in the row cache.
Yeah.
the key cache is a partition cache. Okay.
Yeah, partition key cache. So it has that levels. One is the partition index, and then from that index you go and find out the offset. Then you will be using the other cluster indexes also.
That is fine, but how does this key cache will help? I mean the partition cache.
It contains offset. With that
Mhm.
offset, you will reach to that particular SS table, right? Where that offset is present, and then from there you can read it.
Yeah, so you
It's
can
exactly like LRU kind. Yeah. Yeah, we'll go ahead.
Right. So that exactly what you said. It comes from partition key to this partition summary, and then from partition summary it comes to this index, and from the index it will go to this compression offset, and then to access table. It's a long process though. Yeah, but that is one way. So if you find that partition key, it will directly jump to this compression offset because you know the exact partition key. If you don't know, then you have to go to the partition summary and the partition index to get that. So you have two hops, right? So two levels of lookups. But in this case, it is just directly you go to the compression offset, and from there you come to know in which SS table and which offset that value is. Or maybe the block is right because it's a partition again. So from that block again, you'll have to go again search for that particular because it's sorted. So you come to that range, and in that range you do some linear scan, but that will be not a big one.
Okay, got it. Yeah, thanks.
And secondly, there is nothing called update and delete, right? We can't delete a row in our SS tables, right? So that
tombstones
still
they call it.
Okay, tombstones, yeah. And then once the tombstones, yes.
So yeah, I am not prepared for compaction and tombstones. I thought maybe I'll take it later because I really want to, the way we discussed about this storing in the SS table, there is also a lot of details about it. And I was reading through it. So I thought maybe just take that in the next session along with the tombstones and compactions because there are many things going on. And the SS tables also, they store in the TOC, you have SS table, and then the SS tables are there because there is another layer on the SS tables also. So it's not directly is going to the single SS table. So there are different ways they are storing it, and why I couldn't follow it. So I thought maybe instead of just bringing whatever I understood, let me read it carefully and then come with that. So that is the reason I couldn't focus more on this area. So, but yeah, I'll get it maybe on Monday. I'll finish that along with the compaction and tombstones.
It's anatomy of hidden, right? Yes.
Yeah, there are a lot many things actually. If you look at the book, what we are reading, that also gives a very high level information, but at least it gives a lot of pointers. So, but if we really dig down deep into all these sites, they really share a lot of very valuable information, and it really helps us, yeah, as well as it consolidates a lot of stuff. So we are well informed, well prepared, for understanding more complex topics, right?
Yeah.
Yeah. So yeah, I think he was talking about the secondary index. I'll read on these also, and then we'll discuss that. If anyone wants to add anything before we close this session, Nick, Shashank, you too.
No, I think we have covered most of the stuff. I like one Got it. Only that Nick was asking, like if the data is present on multiple SS tables, right? Then how?
Yeah, so that is what, they have that table of contents, the SS table of contents. So whenever it comes to the compression offset also, that is another level. And then that is the way it is that flow goes in. Yeah, so I'm not clear about that. So let me read it and then come back.
Sure.
Yeah. So I think if you look at the Dynamo and Cassandra, even if they say Dynamo, see, Dynamo is actually more of a concept, right? It's like, it looks like, because it doesn't have a storage engine. Now this, when we are coming to the storage engine, all this part, right? So the SS tables, mem tables, and all those commit logs, that is the real where the data is persisting. And that is very important. And that is was missing in the Dynamo. Rest of the things about how the replication is done and everything, it's slightly different than Dynamo, but at least we are able to follow. But here we are actually dealing with the storage engines now. And that is what differs the key of Cassandra, and what is completely different from Dynamo, which was not present in Dynamo. They said only you can have different storage engines, and then you can make different products out of it, right? Something like that. That is what I understood.
Yeah, even that failure is different, right? Detecting the failure in Cassandra is totally different from the like accurate function you mentioned. Yeah, sliding window interval something.
Yeah, that was very different. Yeah, that was not in the Dynamo, or maybe they didn't explore more, wanted to keep it very short, because surely that will also have an impact there, I think so. Yeah. But yeah, so the key things are, yeah, what you said, that one, how the replication, then how the consistency levels are, and then the major part is the storage engine, which is huge, right? Yeah, so I think we should spend one more session on that. I'll just get more information. I don't want to have something which is not complete, and then maybe on Monday we'll finish this. Okay. Yeah. No one, none questions, then we'll